Hey guys, welcome back. So in this video we're going to be going over the chain rule, and it's actually my favorite technique out of all of them because it is just used so much in calculus, right? So every derivative from now on that we're going to be doing is actually going to be a chain rule. Anything with polynomials, trigonometrics, exponentials, logarithms, anything is actually going to be a chain rule. So let's check it out and let's get started. So here we have the chain rule is used to derive blank functions, right? So when you learn the chain rule, you think that it's just to derive composite functions, right? So you like to think of them as deriving composite functions. But I will soon show you that the chain rule is actually used for every function. It is just necessary, so we don't get the wrong answer when we have composite functions. So you guys may also be wondering why I have this onion here, right? This random onion that I have, which is a very nice picture of an onion actually. And the reason why is that I like to describe the chain rule as peeling an onion, right? So when you start peeling an onion, you start with the outside first, and then eventually you get to the center. And that is the same idea of a chain rule. You start deriving the outside function, and you eventually get to the center function, right? So here we have a big F, capital F of x, and it is described as little f of g of x, right? So in this case, little g is going to be the inside of the function, right? That's going to be the heart of our onion. And how we start deriving this, if you guys see when we apply the chain rule of capital F is going to be, we're first going to derive the outside. You guys see how little f is on the outside. We're peeling the outside layer, and then we're going to derive the inside. So here we actually derive the outside function. We don't mess with little g, we just leave little g right there, and then we go into the next layer, which is going to be the derivative of g, so g prime of x. So that's the idea here, that we start with the outside function, which in this case is little f, and then we go and we derive the inside function, which is g prime, or g of x, right? So you can do this infinite amount of times because g of x can be composed of more functions, and then that can be composed of more functions. So there can be an actual chain rule where you do like 6 different derivatives, right? There's 6 different insides, 6 different layers of the onion that we keep peeling. But none of this makes any sense unless we actually see some examples. So let's go ahead and do that. So here we're actually going to show you why we use the chain rule, right? Because it is just much more efficient and lets us answer so many more derivatives. So traditionally, before we learn the chain rule, let's say I gave you guys f of x equal to x plus 1 squared. You guys will go through the whole long process, which we're going to go through it right now. This is the last time you have to go through this process of having to rewrite f of x so you can actually use the power rule, which is the only thing you guys know up to now, which is x plus 1 times x plus 1. I know you guys have already learned the chain rule, but we're just going to be limited to just the power, right? So we're going to actually have to, now we're going to have to distribute. So x squared plus x plus 1. You guys are beasts at distributing. And now we're going to have to combine like terms. So x squared plus 2x plus 1. And now you guys are finally done. You're going to have to derive f prime of x, or to derive f of x to get f prime of x, and we're going to get 2x plus 2. So that is a traditional way of taking this derivative, right? We can expand it and we do all this stuff. But imagine if I have x plus 1 to the 7th. I'm going to have 7 of these, distribute to 7 of these, combine like terms, and then I'm going to go ahead and take the derivative. That just takes way too long, just way too long for us. And we're now going to upgrade to the chain rule, right? Which, like I said, we're going to peel the onion. So now we're going to look in example B at f of x as a whole different idea. We're going to look at it as a composite function, right? Instead of some polynomial, we're going to have to expand to then use power rule. We're going to look at it as a composite function. And what that means is that I'm going to tell you guys what is the outside function here, right? So here in x plus 1 squared, we actually have a composite function, but we care about first identifying the outside function, right? So we're actually going to break this down real quick, right? So if we have to write this as f, capital F of little f of g of x, we have to first identify our outside function, which is going to be little f, right? And little f is going to be little f is going to be whatever I can input g into to get my f of x. So here I have x plus 1 squared. So what can I input x plus 1 to get x plus 1 squared? So in that case, my outside function is going to be x squared. I know it's a little confusing because I have the lowercase f, and I have the lowercase f here. So let's actually make this f uppercase f. Okay, let's make that uppercase f. So the outside function is f of x, and the inside function, the function that I input, is going to be x plus 1, right? So now we have identified our outside function and our inside function, right? So we can do the chain rule. Later on, we eventually won't be doing all this slow process of actually having to find the outside and the inside. You guys will see how it gets done. So let's derive the outside function, right? So in this case, if I derive the outside function, it's going to be 2x. And if I derive the inside function, it's going to be 1. Now, if I apply my rule that I have up here, my derivative rule, I'm going to have that f big prime is equal to f prime of g of x times g prime of x, right? So that means that f big prime of x is going to be, we're going to input g of x into f prime of x, so it's going to be 2 times x plus 1, because we're inputting x plus 1 into 2x, times the derivative of g prime, the derivative of g, which is g prime, which is 1. And then if we distribute that out, it gives us 2x plus 2, which is exactly what we actually got over here, right? It's exactly what we got over there. But that is just way too long. Like, describe the outside function, describe the inside function, take separate derivatives. That is just way too long, right? We're going to go ahead and actually do it in a much faster way. So now that you guys know what we're actually doing here, we're going to do it a much faster way. And we're going to erase this little line here, and we're going to go ahead and look at it like this. So I'm going to go ahead and erase this right here just to make myself a little space. Okay, so what I'm actually going to do is I'm going to use my finger to cover the inside of the function, right? So I'm going to put my finger over x plus 1. So in essence, you guys are putting your finger over x plus 1. So x plus 1 does not matter. You guys are putting your finger right there where I had the green. And you're going to derive that function, right? It's a parentheses squared. So if you guys know from the power rule, a parentheses squared is just going to use the power rule. So you're going to bring down this 2. So now when you take the derivative of f, you're going to bring down this 2 and leave your parentheses, right? So now you still have your finger over the x plus 1. And then after you have done that, you have 2 and then you have 1. You still have whatever's in here untouched. You don't touch the inside of the parentheses. You're going to derive your parentheses. And the derivative of your parentheses is going to be 1, because the derivative of x plus 1 is just 1 for the x and 0 for the 1. So the derivative of this whole thing right here, it is just 1. And then you input where you had in your parentheses before, and you have x plus 1. Now when you simplify this, it just gives us 2x plus 2, which is exactly the same thing we did over here. So I know the first way we did this was a lot more formal. We identified the outside function, the inside function, we derived each, and that was just like a very nice formal way. But what we actually want to do here is we just want to be quick at it. We want to just use our finger to cover the inside function, derive the outside function, be like, okay, what do we have inside? Let's derive this inside function now. Are we done? Sure we are. Boom. Let's move on to the next problem. Alright? So if it's still a little cloudy, it may be, I understand, the chain rule is actually pretty annoying and has a lot of steps to it. So what we're going to do is we're going to do lots of examples in the chain rule. So by the end of 5 or 6 examples, you guys just got this. So let's go ahead and do example C, which brings us to our next point. Whenever we're deriving anything, product rules, quotient rules, chain rules, regular power rules, we never like radicals. Radicals are just not our friend. So what we're going to do is we're going to go ahead and before we even derive, we're going to change it from a radical to an exponent. And if you guys remember, a square root is the equivalent of what exponent? 1/2. That's correct. So a square root is equivalent to the 1/2, and that is the exponent that we're going to use. Now we're going to go ahead and use the finger method. No longer we're going to identify no outside function or inside function. We're going to use the finger method. So let's put our finger over, let's put our finger over the parentheses. We're just covering the parentheses, and we're going to derive the parentheses. So we have a power that is 1/2, and we're going to bring it down. So we're going to have 1/2 x cubed minus 2x plus 1, and then 1/2 minus 1, which is just negative 1/2. So we leave the inside of the parentheses alone. It is just the inside of the parentheses. It is just x cubed minus 2x plus 1. We just leave it alone. And then, now that we're going to uncover the parentheses, we're going to derive the parentheses. There's a minus that I got erased. Sorry about that. And now we're going to derive the parentheses. And the parentheses, the inside of that gives us 3x squared minus 2x. So what we're doing is we're first covering the parentheses. We're doing the power rule, so it's 1/2 to the front. Don't worry about the parentheses. 1/2 minus 1 gives us negative 1/2. And then we look at the parentheses and we're like, okay, let me derive you. Boom, derived you. So we're peeling the onion from the outside to the inside. So we're getting from the outside function to the inside function. And now, which is actually what I say the toughest part, is cleaning up the derivative, right? The algebra behind it is just really annoying. So a big no-no that we identify is this negative exponent. We don't like negative exponents, so we're going to go ahead and make it a positive exponent. So how are we going to do that? Yes, we're going to bring it to the bottom. So it's going to be x cubed minus 2x plus 1 to the 1/2. We just brought it to the bottom. And now we're just going to scoot. We're going to scoot this right here to the top, because it's multiplying, so we're just going to scoot it to the top. It's going to be 3x squared minus 2. And now, we're going to be very, very annoying, and whenever we leave our derivatives, we do not want to leave them whenever we have any exponents that are fractions, right? So what we're going to do is, any fractions that we identify, like this x to the 1/2 here, this 1/2 fraction exponent that we have, we're going to get rid of it, and we're going to make it go into a radical. So we're going to rewrite this whole thing, 3x squared minus 2 times 2, and then we're going to have radical of x cubed minus 2x plus 1. So you guys can see this x to the 1/2 or this square root of x, it's just used interchangeably all the time. So whenever we start a derivative, we don't want to start with radicals, but we want to end with radicals, right? So you kind of go through this whole mess of going from the radical to the exponent. We derive an exponent, and then after we get an exponent, we don't like a negative. We don't like negative exponents, and at the end, we don't like exponents at all. So we start with radicals, we change it to exponents, and then we derive, and then we finish with radicals, right? So where we start and finish with radicals, but the in-between is always done in exponents. And that can be our answer to be our f prime of x. And my notation actually is off here, so I apologize. I started deriving here at this step when I brought the 1/2 down. So this deserves a f prime, this deserves an f prime, and this is also an f prime. Notation is very key. Whatever your f is, it's your f, and whatever your f prime is when you have started taking your derivative. Okay? And all the way through your simplification, that is always your f prime. It is not going to change. So now, let's go ahead and do this letter D, which is going to be a product rule, but that it has chain rule in it to do its individual derivatives, right? So it's going to get a little more tricky here. So the first thing we do is we check for radicals. We have no radicals. We can just jump straight into our derivative, right? So f prime of x. And now we're going to go ahead and ask ourselves, right? How do we do the product rule? Yes. We start off by deriving the first function. So now we're going to derive this function, which is the first function. And guess what? That first function is a chain rule. And what is my indication that that's a chain rule? The fact that I have a third outside. So that I have a third outside means that I have a chain rule, so I need to compute that chain rule. And how am I going to start? By putting my finger, so here I'm going to do the chain rule of that 2x plus 1 to the third. I'm going to put my finger over this 2x plus 1, putting my finger over it. I have a parentheses to the third. What am I going to do? I'm going to bring down the third to the front, leave the parentheses by itself, doesn't matter what it is. 3 minus 1 is 2. That is, I'm just computing my power rule. Now let's put the parentheses back in there. 2x plus 1. Right? So now we look at it. We have 2x plus 1. Now that we have taken the derivative of the outside, we have peeled the outside layer of the onion. We're going to take the derivative of the inside layer of the onion, the next layer that we have to deal with. And that is 2x plus 1. And what is the derivative of 2x plus 1? That is 2. So we're going to multiply by 2. Okay? So the derivative of the first function is right there in green. Now we're going to multiply this whole thing by the second function, which is just, let's leave it in blue, x squared minus 1. There's going to be a giant plus in between them because it's a chain rule. I mean, it is a product rule, so product rules use plus. And now we're going to do the derivative of the second function, right? The second function, which is x squared minus 1. Is this a chain rule? Nope. It's a simple power rule. So the derivative of x squared is just 2x minus the derivative of 1. The derivative of 1 is 0, so it doesn't even matter. We just kind of leave it as 2x. Let's kind of close it up. So we're done deriving the second one. And now we're going to multiply it by the first one, which we're going to do in green, which is going to be 2x plus 1 to the third. So now we are done. We have started by deriving the first one, multiplied by the second, throwing a plus in there, deriving the second one, multiplying it by the first one, and that is exactly how we do our product rules. Then this was a complicated product rule because there was a product rule with a chain rule as one of our derivatives, right? So that's what we had to keep that in mind. So now the most annoying part, kind of putting it all together and simplifying. So let's go ahead and do that. So we're gonna have f prime of x, and now what can I simplify here in this first term? I have a 3 here that's multiplying with this 2 here, so I'm going to have a 6, and then a 2x plus 1 to the second power times an x squared minus 1. Okay? So I'm done with that. Now I'm going to add. Can I simplify anything here? Not really. Nothing is adding. I mean, nothing is multiplying. No numbers that I can multiply with each other. No x's outside. Just 2x times 2x plus 1 cubed. And I can get a little more technical here because the simplification of this problem can get just a little more intense, right? So I would say that now when we've gotten to this step right here, we're actually done, right? But I'm going to take this opportunity to be able to just kill it when it comes to simplification, right? To show you guys all the simplification that could be done on this problem, right? So a lot of times when you're given multiple choice answers, the hardest part is not even taking a derivative. The hardest part will be actually making your answer fit the choices, right? So that's what I'm going to do here. I'm going to give you guys a derivative which I think is fully done. You have fully done your derivative here. You even went one step ahead and multiply the 3 times the 2. But let's say you wanted to go ahead and kill the simplification. I'm going to show you guys how to get that done right now. So we look across, right? So let's start with the numbers. We have 6 here and we have 2. We start with the numbers. Can we factor out anything between a 6 and a 2? Yes, we can. We can factor out a 2. Correct. Right? So now what we're going to do is we're going to have something like this. Okay? So we factor out a 2 from the first term. So that means that we have a a 3 left here. We have a plus between them. We have a plus between them. And then since we took out a 2 from the second term, we just have a 1. Okay? So we have taken care of simplifying and taking out the greatest common number. Now let's look at the 2x plus 1. Can we take anything out? Can we take out 2x plus 1s? And the answer is yes. Because we have 2x plus 1s on the left hand side. And then we have 3 2x plus 1s on the right hand side. So how many 2x plus 1s can you take out? Okay, we can take out 2, right? Because we take out the least amount from the 2 of them. So since the first term has 2 and the second term has 3, we can only take out 2 because we can't take out 3 because then the first one doesn't have enough, right? So we take out the least of the two numbers. Between 2 and 3, we take out 2. So we can easily say that we can take out 2 factors of x plus 1, of 2x plus 1, right outside. So if I'm going to take out 2 from this guy, if I take out 2 from this guy, I'm left with none. Cool. So the 3 here just is chilling by itself. And then if I take out 2 from this, 3, how many do I have? I have 1 left. That is correct. So let me go ahead and put 2x plus 1. Okay, so now let me go ahead and check now factors for, do they all have an x? I mean an x squared plus minus 1? Well, this guy has an x squared minus 1, but the second factor doesn't have an x squared minus 1. So in this case, the x squared minus 1 just stays with the first term. We cannot take it out. It just stays there. And now when we look at the second term, we see that it has an x that we have yet to take out. Does the first term have an x? No. So what happens is that the second term just stays with that x, right? So this may remind you a little bit of college algebra or pre-calculus, because what we're doing here is we're just taking out the greatest common factor. So now we're done with the calculus, which was just take the derivative, take the chain rule, take the product rule, do the power rules. We did all the rules for calculus, but now what we're dealing with is still the same old college algebra. So, and now you want to say you're done here, but guess what? We're not. So let's go ahead and keep going. So this outside right here is pretty simplified. Nothing else we can do here. And we always take factors over expansion, which means that if I have 2x squared plus 1, I don't want to expand this and for this. I want to leave it factored. Factors always goes over expanded. So in this case though, I have 3 times x squared minus 1 plus 2x plus 1. This is not like nicely factored. It looks like very ugly because we have like all these terms. So I want to make this all just one nice long polynomial, right? So what I'm going to do is I'm going to distribute this 3 to both sides here. So I'm going to get 3x squared minus 3. And then I'm going to distribute now this x here, both of these. So here I'm going to get plus 2x squared plus x. So now you want to think you're done, but we still got to combine like terms inside of that. So the outside here is just done. It's been done for a while. But inside of this brackets, we still got to combine like terms. So we have 3x squared with this 2x squared. So that combines and gives us 5x squared. Then we're going to have, I'm going to spot out this x here because I want to go in decreasing order. I'm going to have this x here, so I'm just going to bring this x here to the front. And then I'm going to spot out the last term here, which is minus 3. And I'm going to just bring this guy to the back. So now I can say that I'm completely done with my simplification of my derivative. So now, even if you didn't have to go this far, you're ready for any multiple choice setting of this answer. And professors like when you actually have done all this crazy algebra work because it just shows that you're dominant and you're confident in your math skills. Now that you're just kind of like putting it together and hopefully you can just get the answer. Here you're showing complete domination over this problem. I know you don't care about it, but professors do. And it's all about pleasing your professor because that's who gives you your grade. So now that we did this and we discussed that the calculus ended at this part, right? So the calculus actually ended here, and then from here down, it was just algebra, it was just pre-calculus, it was just a lot of simplification, right? So You guys see how intensive derivatives actually is when it comes to algebra. And let's go ahead and try out another example, which in this case, we're going to mix what we learned already with the quotient rule with the chain rule. So now, every new derivative that we're doing, they're old skills that we learned, product rule, power rule, quotient rule, but now we're throwing in a new trick, which is going to be the chain rule. And we're going to go about it like the onion, right? So let's go ahead and start E, in which we inspect the function for radicals. And we find one on the top. So what we're going to do is we're going to rewrite the function to make it radical-less. It's a new term I just introduced there, radical-less. And it's going to be x minus 1 on the bottom because the bottom has no radicals. And then we have cube root, right? So cube root changes to x plus 2 raised to the 1/3. Okay? So now that we have changed it from a radical to an exponent, we're going to go ahead and derive it. And we're going to derive it in the style of a quotient rule. Because we notice that two functions are dividing. So whenever two functions are dividing, we're going to use our quotient rule. So let's go ahead and say derivative because we're about to derive. And let's hope this is not as ugly as the other one that had so many steps, right? So let's go ahead and let's hope this is nice and pretty. So let's go ahead and now just derive. We're going to start off our quotient rule by just making the bottom squared. It's the easiest step of the quotient rule. We'll just make the bottom squared. And now, we always start the quotient rule just how we start the product rule. Remember, the difference between a quotient rule and a product rule on the top is there's no difference. The only difference is going to be the sign. So only the signs change. That we're actually going to have a minus somewhere in between the two terms. Okay? So we start off by deriving the first function, which in this case is going to be this x plus 2 to the 1/3. So we start that off by peeling the onion, right? So here we have x plus 2 to the 1/3. So we see that it's a chain rule because it's a composite function we see in there. We have an x plus 2 function being raised to a 1/3. So that's like too much going on for it to be a simple function. It's a composite function. And we're going to use the peeling the onion method. So what is the outside function? What is the first peel that we're going to do with this onion? And that is going to be our parentheses, right? Where we just kind of like cover this. It's going to be our parentheses raised to the 1/3. Our outside function is this 1/3 exponent here that we're going to bring down. So let's go ahead and do that. So we're going to have 1/3 just brought down. Let's give myself a little space for it to make sense. So 1/3 brought down. And then we're going to leave our parentheses the same way it is. And then we're going to subtract 1 from the 1/3. So I know this part is always a little bit annoying, but the good thing is that when you're deriving all these things, you're going to be doing the same kind of subtractions. 1/2 minus 1. 1/3 minus 1. 2/3 minus 1. It's going to be the same kind of thing, right? So eventually you do it so much that you just kind of memorize what it is. You do it like subconsciously. You're just like, okay, this is the answer. So 1/3 minus 1. So 1/3 minus 1 is the same thing as 1/3 minus, I'm going to rewrite 1 as 3/3, right? Because anything over anything is 1. So I'm going to write it as a 3/3. And now I have my common denominator here. And that's going to give me 2/3, negative 2/3. So you guys can see that you're going to be doing the same kind of subtractions. You're mainly going to be doing 1/3 minus 1 or 1/2 minus 1. In those cases, you guys are going to be doing so much practice that you guys already know the answer without even having to think about it. Okay? So we're going to have here to the negative 2/3 because we just subtracted 1. Now we put the inside back in there, which is going to be x plus 2. I kind of ate the plus here. And we're going to multiply to the derivative of the inside. What is the derivative of x plus 2? And that is going to be just 1. So we're done with the derivative of the first. So now we're going to write the second, which is just, the second function is the bottom in this case, which is x minus 1. Minus, and now it is turned to, we started by deriving the first, multiplying it by the second, which in this case the second is the bottom. Our second function is the bottom. And now we're going to derive the bottom, or the second function, which the derivative of x minus 1 is just 1. And now we're going to multiply by the first, which we're going to have it in red. I hope all these colors kind of like help you guys out, because we know that we're deriving the first one in red, and then we're just multiplying by the original one at the end in red. And then we're in between, we are playing with the second function or the bottom function, in which we start off by just rewriting it the same way it is, and then after the minus sign we actually derive it. So we're done with the calculus. Boom. We're done with this chain rule. Now what we got to do is we have to make sure that we can simplify it. So let's go ahead and simplify it. So what that means is that I'm going to go ahead and I'm back. And then what I'm going to do is I'm going to go ahead and play with this stuff. And what is the first thing that tells me that it's something needs to be done is the fact that I have this really annoying negative exponent here, right? So I have two things that I don't want. I have a negative exponent, and I also have a fraction as an exponent. So that's like big no-no. I need to get rid of that ASAP. So I'm going to have f prime of x is equal to, my bottom is going to be worryless. I'm just going to have x minus 1 squared. No problem, this is my bottom. But then I'm going to have to deal with my top, right? So the first thing that I'm going to do is I'm going to rewrite this fraction with a positive exponent. So it's going to be x plus 2 to the positive 2/3, right? And I'm going to bring this x minus 1, just multiplying it to the top, to just x minus 1. And we have not forgotten about this one here that's multiplying. That one there that's multiplying, that's not going to make a difference. So we're just going to forget about it, actually. And then now we're going to have our minus sign. And then we're just going to have our x plus 2 to the 1/3. So the first thing we did was we did our derivative, and then we got rid of negative exponents. So now we did our negative exponent check, right? So now after we do our negative exponent check, we're going to go ahead and do our fraction exponent check, right? So that means that no fractions, our exponents we cannot have fractions on our exponents. So let's go ahead and do that. So then we're going to have f prime. The bottom is just going to be there by itself, just hanging out. Right? And then we're going to have x minus 1 with a 2 right here. And then 2/3 is going to be the same thing as having x plus 2 to the second. And then this 3 here that's on the denominator is going to come to the front, and it's going to make this I'm going to make this in green, so we can say that this 3 here becomes the 3 here as the third root, right? So we have a 3 there as a third root. And I'm going to make that 2 in the front a little bigger so we don't confuse them. So you guys see how the 3 from the denominator became our third root. And now we're going to go ahead and just have our minus sign, and then we're going to change this x plus 2 to the first, and then this third is going to come to the front, and it's going to be our third root, right? So we're safe to say that now we're done, because we have changed things into radicals, and we have gotten rid of our negative exponents and all that stuff. So we're safe to say here that we're done. It looks really ugly because we have one that's a fraction and one that's not a fraction. So that's the annoying part. And they're all being divided by this one thing. But you're safe to say that you're done here. The algebra from here to simplifying it even more is kind of crazy. But I'm going to spare you guys that algebra and just give you guys some practice problems where you guys are going to be forced to try it on your own. So in the practice problems after this, we're actually going to try out some chain rules that they're going to have all these annoying exponents and radicals. So you guys can get a lot of practice on making them fit the multiple choice answers that we have. Alright? So that's going to prepare you for any multiple choice tests that you guys may have coming up working on derivatives. Because the most annoying part is always the algebra that is going to happen with all these derivatives that we take, because all these radicals and all these exponents go on. So let's go ahead and try some practice, and I'll see you guys next time.